For the Unit 12 test, for the definitions, be sure you remember to skip lines, underline, and number as you go through those. About half of your test will be either definitions or facts in the no section of this. So be sure that you look over those and study them as well before your test. For the combined gas law equation, remember we have our P1 V1 over T1 equals P2 V2 over T2. So it's pressure, volume, and temperature. Temperature has to be on the bottom, and temperature has to be in Kelvin. The pressure and volume can be in various units, but they have to be the same on both sides. So if pressure is millimeters of mercury on one side, it has to be millimeters of mercury on the other side as well. Whenever you look at each one of those relationships, we get our individual gas laws. So one of the things to know here are the laws included in that combined gas law. So for Charles's law, remember Charlie Brown is on TV, so that's going to be temperature and volume. And if you write them in that order, that's not correct. We'll put volume over temperature so it matches our combined form. And so we see then that that is a direct relationship between those two. You do need to know if the two variables are directly or indirectly proportional. Another law that we have incorporated in our combined gas law is the Gay-Lussac's law. Remember, guys like power tools, so that's going to be the pressure and temperature. And that is also a direct relationship between those two variables. And then our final one is Boyle's law. Boyle's have pus and volume, so that's pressure and volume. And since they're side by side there, we have an indirect relationship between them. When one increases, the other decreases. So they're indirectly or inversely proportional. For our ideal gas law equation, we have PV equals nRT. And remember, if you're not given the number of moles, if you're given grams instead, we can write that a little bit differently. We can have mass over molar mass for the number of moles. And if you go ahead and separate it like this, it makes it a little bit easier for you to do your math. The M on the bottom is the molar mass. You also need to be able to use your density formula. Remember, density of a gas, it's nitrite. Pressure times our molar mass. Let me write my M a little different. Pressure times molar mass over RT. So you can find the density of a gas and it'll be in grams per liter whenever you solve for that density. For all of these, R, remember, is our ideal gas law constant. It's 0.0821 liter atmospheres per mole Kelvin, or latum molk, if you say it all together. For the assumptions of kinetic theory, there are two assumptions here. We're going to assume the gas has no volume. And we're going to assume that the particles are not attracted to one another. Now we know there's no such thing as an ideal gas. We have our conditions at STP. So that will be 0 degrees Celsius and 1 atmosphere. We might need to use different units, so that would be 273 Kelvin or 760 millimeters of mercury. And then our phase changes. You can go back and review in the very first unit of the year, Unit 1, if you need to look back at freezing, melting, condensating, sublimating, boiling, condensation, all of those. Okay. So on the front here, these questions are just looking at the relationships between them. So in number 1 here, if we add more gas to the container, there's more particles in there bouncing around, hitting the side of the container, so pressure will increase. We're assuming here that the temperature and volume do not change. So the only thing that could change is the pressure. If more gas is inside, then you get more pressure on the sides of the container. Number 2, we have gas being compressed, so it's in a smaller volume. We want to know what happens to the pressure. You can think about the particles and how they're involved there, or we can also think about our gas law. If we want to look at that, P1 V1 over T1, and we're dealing with volume and pressure. If the temperature remains constant, remember pressure and volume side by side are going to be indirectly proportional. When one goes up, the other has to go down. So if it decreases from 4 liters to 1 liter, then the pressure has to do the opposite. The pressure is going to increase. And it increases because there's less room for the particles to move. So they will collide more often with the container walls. They're all bouncing around in there, and if there's less space, they'll hit it more often. For number 3, we have a gas with a volume of 4 liters allowed to expand. So kind of the opposite here. What's going to happen to the pressure? If the volume is greater, now our pressure does the opposite. It decreases. There's more room for those particles to move around. So they will collide less often with container walls. This is the opposite of what we saw in number 2. Number 4, you're heating a gas. So that means that our temperature is increasing, and we want to know how it's going to affect the pressure. So remember, pressure and temperature are directly proportional. When one goes up, the other one goes up as well. So temperature goes up, pressure increases along with it. If we think about how those particles are moving, you add more heat or you add more energy to those particles, they're moving around faster. So our particles move faster. So they collide more often with the container walls. On your test, you'll be given some different circumstances, and you can think about how the particles are moving. You can think about the equations to figure out how changing one variable will impact another. Okay, for the problems, we actually have to plug in some numbers and solve them here. So for the first one here, we can start with our combined gas law. And if we don't need all 3 parts, then we can get rid of one of them. So we have a pressure of 2.5 atmospheres. It's at 25 degrees Celsius. We want to be sure to remember to add the 273 to change it to Kelvin. What will be the pressure? So P2 is what we're trying to find at 250 degrees Celsius. So that's our second temperature. Again, don't forget to add our 273. So it does not mention volume at all. So we can get rid of that volume. Since it is dealing just with pressure and temperature, this is going to be Gay-Lussac's. You have to be able to recognize which one of your gas laws is being used. And we want to solve this for P2. So when we rearrange this, we get P1 T2 over T1. So our first pressure was our 2.5 atmospheres. Our second temperature is going to be 523 Kelvin once we add the 273. We'll divide by our initial temperature, which was 298 Kelvin. Our Kelvin units will reduce or cancel. We'll be left with atmosphere, so we multiply and divide, and we will end up with 4.4 atmospheres. Okay. Problem 2, we have some gases mixing together to give us a total pressure of 250 millimeters of mercury, and it tells us the partial pressure of oxygen is 50. The partial pressure of nitrogen is 175. What is the partial pressure of carbon dioxide? So to find our total pressure, we're adding together three gases. We've got oxygen, we've got nitrogen, they're both diatomic, and then we've got carbon dioxide. This is going to be Dalton's law, and I didn't leave much room. Dalton's law of partial pressures. So we can fill in our numbers here. Our total pressure was 250 millimeters of mercury. We just want to make sure everything's in a common unit here. Oxygen was 50, nitrogen was 175, and we don't know this last one. So we'll subtract. We have 250 minus 50 minus 175, and we will be left with our pressure of carbon dioxide as 25 millimeters of mercury. You might also have this rounded to 30 because of how we're looking at significant figures. That 50 is only significant to the tens place. So either one of those. On your test, you would only have one that would be anywhere close to the correct answer there. Number 3, we have 5 liters. Liters is going to indicate that we have volume, and it's at negative 50 degrees Celsius. Don't forget to add 273. You'll never have a negative number if it's in the Kelvin scale. And it's warmed up to 100 degrees Celsius. So that's our second temperature. Add our 273 to it. What is the new volume? So V2 is what we're trying to find if the pressure remains constant. So we're dealing with volume and temperature, or TV. Charlie Brown is on TV, so this is Charles's law. We'll start with our combined gas law. So P1 V1 over T1 equals P2 V2 over T2. And we want to solve for V2, and we are not dealing with pressure at all. So we rearrange that. Our second volume will be volume 1 times T2 divided by T1. So our first volume was our 5 liters. Our second temperature was the 100 plus our 273, gets us 373 Kelvin. Our first temperature was at negative 50, so negative 50 plus 273 gets us 223 Kelvin. Our Kelvin units will reduce, we'll be left with liters, and if we round to two significant figures, because of the negative 50, we end up with 8.4 liters. That would be our second volume. Number 4, we have a 7.0 liter air sample, that's volume. It is at a temperature of 20, pressure of 800 millimeters of mercury. What will be the volume? So V2 is what we're trying to find at STP, which means that our second temperature, if we keep it in Kelvin, will be our 0 degrees Celsius, so 273 Kelvin. And then our second pressure is 1 atmosphere for STP, but it's in millimeters of mercury on the other side, so we're going to put 760 millimeters of mercury. So we are going to use the entire combined gas law. There's nothing that's not used here. We have pressure, volume, and temperature. So we have P1 V1 over T1 equals P2 V2 over T2. And we want to solve for V2. So we have to move T2 to the other side. So we got P1 V1 T2, because we have to multiply. It's the opposite of division. And then we'll divide by P2 on the other side. So we end up with that rearranged formula for volume 2. So then we can plug in our values. Our first pressure is our 800 millimeters of mercury. Our first volume was 7 liters. And then you have to be careful here, it switches to the second temperature on top. So at STP, 0 degrees Celsius, is 273 Kelvin. Our initial, or our first temperature, was going to be 293 Kelvin once we add in that 273. And then our second pressure was at an atmosphere, or 760 millimeters of mercury. We had to make sure our units were where they would cancel. And so when everything reduces, we're left with liters. And if we round this to only one significant figure, because of this 800 right here, we end up with volume 2 equal to, again, 7 liters. It's really about 6.8, but because we can only have one significant figure, it rounds to 7. Okay, number 5, we again have all three of our variables, so we will be using our combined gas law. We'll have P1 V1 over T1 equals P2 V2 over T2. You need to have that memorized for your test. So we've got a gas with a certain volume, temperature, and pressure. It's allowed to expand, so we know this is how it's changing. It expands to that volume, so that's V2. Make sure they're both in liters. They are. They could be in milliliters, but they'd both have to be in milliliters. The final pressure is 425. That's the same pressure unit we had in the other one, so that's good. What is the final temperature? So T2 is what we're trying to find. So if you're trying to solve for T2 here, we're going to end up moving it to the other side and then moving some of the stuff back there. So T2 is going to equal P2 V2 times T1 all over P1 V1. So our second pressure was 425 millimeters of mercury. Our second volume was 8.2500 liters, very precise. And our first temperature, we add 20 plus 273, we get 293 Kelvin. Our first pressure, 650 millimeters of mercury. Our first volume, 3.50 liters. We'll get liters and millimeters of mercury, so we'll be left in Kelvin. It did not say what was the final temperature in degrees Celsius, so we can just plug that into our calculator. Remember, you're dividing by both things on the bottom, both the 650 and the 3.5, and we end up with temperature 2 equal to 452 Kelvin once we round it to our three significant figures. Number 6, we notice something that was not included in all the others so far. We have this 12 grams. So we have the mass given. Anytime we're given mass or moles, we know we have to use our ideal gas law equation. So this is going to be the ideal gas. And so that's the PV equals nRT, or if we have mass, it'll be MRT over our molar mass. So we have 12 grams of oxygen. Remember, it's diatomic. And it's at 25 degrees Celsius. That's our temperature. Remember, nothing is changing, so it's just T, not T1. We have a pressure of 0.2 or 0.520 atmospheres. And because of the units on R, we do have to have volume in liters if we're given that. And then we have to have our pressure in atmospheres and temperature in Kelvin. So we want to solve for volume. So we want to solve for V. So we're going to have to move P over to the other side. So we have mass times our constant times temperature over our pressure and molar mass. So our mass given is 12 grams. R is our 0.0821 liter atmospheres per mole Kelvin. Our temperature is going to be 273 plus 25, or 298 Kelvin. Our pressure is 0.520 atmospheres. And our molar mass, we look up oxygen on the periodic table, we get 16.00, but it's diatomic, so we multiply by 2, and we get 32.00 grams per mole. Those are the units for molar mass from our table. So we get atmospheres that will reduce, we'll get grams, we'll get Kelvin, and we'll get moles. So everything reduces out except for liters, which is a good volume unit. So we multiply on top, divide on the bottom. We end up needing only two significant figures because of the 25 degrees. So we end up with 18 liters. On number 7, We are also given moles. So this is when we use our ideal gas law equation. And this time they did go ahead and give us moles, so we don't have to use the altered form of it. We can just go ahead and use PV equals nRT. What pressure, so P is what we're going to try to solve for down here. We have our number of moles. We have our temperature. We have the volume. We have to be careful. Remember, we need to have that in liters. So there's 1,000 milliliters in a liter. You move your decimal 1, 2, 3 places back, and we end up with 0.65 liters. And we didn't have a decimal at the end of that number, so the 0 would not be significant. So we rearrange this for P, which means we're going to need to divide by our volume on this side. So we rewrite that pressure equals nRT over volume. So our number of moles, 0.450. We won't have to look anything up on the periodic table since they did go ahead and give us moles. We have our gas law constant, 0.0821 liter atmospheres per mole Kelvin. Our temperature, we add 273 to the 55. We get 328 Kelvin. And then we divide that by our volume once we change it into liters. And we'll round our answer to 2 significant digits because of that 650. Our liter units will reduce, our moles will reduce, and our Kelvin will reduce. So we'll be left with atmospheres, which is a good pressure unit. And we end up with 19 of those atmospheres. They are not ATMs, they are atmospheres. Number 8, they give us the density of our gas, so we have to use our nitrite. Density is PM, that's the pressure times molar mass, over the gas law constant times the temperature. And this time we're trying to solve for the molar mass. We want to solve for this M right here. We have the density given, 0.762 grams per liter. We have the pressure in atmospheres, which it has to be for our constant to be used. We have our temperature. Just remember to add 273 to it. And if we rearrange our equation to solve for M, we end up with dRT over P. So our density was our 0.762 grams per liter. R is our constant, liter atmospheres per mole Kelvin. Our temperature, we add 273 and we get 298 Kelvin. And then our pressure has to be in atmospheres, and it is 0.634 of those. So our atmospheres will reduce. We've got liters. We've got Kelvin. We're going to be left with a gram right here and a per mole right there. So when we end up with our answer, it'll be something grams per mole, which is a molar mass unit. And we end up with a value, 2 sig figs here because of the 25. We get 29 grams per mole. So about half of your questions on your test will be definitions, knowing which laws are which, looking at just general relationships, knowing conditions of STP. And then the other half will be doing some of your basic conversions between the different pressure units. We'll give you the information that 1 atmosphere is 760 millimeters of mercury. It's the same as 760 torr, or 101.3 kilopascals. We'll give you those conversions. You just have to be able to use them to convert a few values. You have to be able to convert between degrees Celsius and Kelvin. The other half of your test will be working these problems using our different gas laws. They are multiple choice problems, but you just have to be able to work them out using the different equations. You have to have those memorized. You will also have a few questions on reading a phase diagram and labeling different parts of it. So when we look at this phase diagram, remember we have our 3 states of matter starting on the left and going around clockwise. We'll have our solid, liquid, and gas. The point where we have a temperature of 216.6 Kelvin and a pressure of 5.2 atmospheres, where those meet here in the center, that is called our triple point. And let's go ahead and jump to D. The critical point is going to be at the end of this line between liquid and gas. That's our critical point. Beyond that critical temperature, it will not be a liquid like we think of it. It will be a supercritical fluid. And so that temperature is going to be 304.25 Kelvin. And the critical pressure, we just read that line over, and we get 73 atmospheres. So going back to C, it says at 10 atmospheres, the temperature moves from 200 to 225 Kelvin. What phase changes this? So you have to estimate a little bit. 10 is going to be a little bit up above where 5.2 is. And we're going to go from 200, which we've got 197 and 216. So 200 is going to be closer to the 197, so somewhere around in there. And then we're going to 225, which is going to be a little bit beyond our 216. So we're going to go across here. So from a solid to a liquid, it helps if you think about water. If you have solid water, ice, and it becomes liquid water, then we call that melting. The normal boiling point will be where it forms a gas at our normal atmospheric conditions. We have 1 atmosphere worth of pressure above us, and I know this is not actually boiling because it's going to go directly from a solid to a gas at this point, but it's still the point at which it is vaporizing. It is turning into a gas. So that's going to be at 197.5 Kelvin. Be sure you look over your definitions, the information to know, and that you can work with the different formulas.